We're now going to look at how we can factor or find the zeros of these higher degree polynomials. So we have something that's called the rational root theorem, and we'll start with the easier case. And so it's stated here loosely. The rational zeros of a monic polynomial, so a polynomial whose lead coefficient is 1, which means it starts with x to the something, nothing out front, and with integer coefficients. So all of those numbers that you'll see should be integers. It'll be of this form that's written here, and that form is really important. So x to the n, there's like an invisible 1 out front, plus an integer times x to the n minus 1. It could be 0, and then it's integer times powers of x all the way down to a constant term. And so if we have a polynomial that's written like that, then all of those rational zeros are actually, in fact, all integers, and they'll all be integers that divide into or are factors of that constant term, so the last term in that sequence, the a naught. So we'll start with an example of something that should be doable with previous math techniques. So what we've got here is a second degree polynomial. P of x is x squared minus 2x minus 35. And what we're going to be able to do here is actually find all of find all the rational zeros of this. And we should see that it's consistent with this theorem. So we can actually solve this by factoring. And if you remember, for these ones, these are the monic ones where there's the lead coefficient is 1. The technique's a little bit easier. We just need two numbers that add up to the middle term, -2, two numbers that multiply to the last number, -35. So we want a product of 35 and a difference of 2. So my numbers are 7 and 5. And it'll be -7 to make that -2. And so if you remember this one, we can jump right into the factorization, and we can actually write x minus 7 and x plus 5. And so if we're solving for the zeros, we're basically solving the equation P of x equals 0. Well, that means that x minus 7, x plus 5 are 0. And then if you remember, what that means, if it's factored like that and it's equal to 0, it means that at least one of the factors must be 0. So either x is 7 or x minus 7 is 0, which means x is 7, or x plus 5 is 0, which means x is -5. So these are our zeros. The 5 and, -5 and 7. And then we can actually just check with the statement that it's consistent with what I've said here, this theorem. So in this, what we would have is our a naught is that last term, the constant term, so it would be -35. And then what we can see is that both 7 and -5 divide evenly into -35, right? 7 times 5 is 35, so they are both factors of it. And it doesn't really matter if things are positive or negative. That's not going to affect divisibility, basically. So this would be a first example. So now we want to see how we can actually use this theorem. Okay, so for the second question, we're not going to be able to actually find the zeros for this because I've given you a polynomial that's missing some information. So instead, what I'll ask you is a terminology that I'll use pretty frequently. I'm going to ask you to list all of the potential rational zeros of this P of x equals x to the 5. So you'll see here, it's monic. It's what we're hoping for, right? There's an invisible 1. It's 1 times. Plus, I don't know what any of those middle terms are. And then we have -42, so that's my last term. That should be my a naught. So yeah, if we want to use this theorem, then basically what we're going to do is use the fact that the rational zeros are going to be integers that go into -42. So the way that we can do this is just list the factors of 42. And then we need all plus or minus of them. So I'll just usually write this in a really particular way. Just for a short form, I will write PRZ for potential rational zeros, and it's going to be this set. I need all the positives and negatives, so I'll write a plus minus because that's what that usually indicates. And then my set notation, because I'm going to write out a list. And this list is going to be my factors of 42. You can start down at 1. I mean, 1 goes into everything. And then I know it is actually 1 times 42, so maybe I'll write that at the end of my list. 2 goes into 42 because it's 2 times 21. 3 does go into 42. I can tell that because I know 3 goes into 21. So it should go in, it'll be 30 plus 12, so that should be 14. 4 does not go into 42 because it goes into 40, and the remainder of 2, it won't go into that. 5, no. 6, yes. It's 6 times 7. And then the next number is 7, and I'm already there. So I should have at this point all of my pairs of factors. And yeah, that's gonna be my list. It's all of the integers that can possibly go into that. So this is it. Obviously, we probably won't have all of these being actual rational zeros. So that's one note. These won't all work. Actually, in fact, something else that I'll be using in some of the later lessons, there's actually at most 5 different zeros. And that just comes from the fact that the degree of this polynomial that I've given you is 5. And remember, if there's a 0, that means that some factor x minus a can be pulled out of it. Well, I can only multiply 5 different x minus a's together to get something that has degree 5. So there's only at most 5 zeros. And then something else to list here is that there may be irrational zeros. Like if you use the quadratic formula, you know that sometimes you get roots that come into your answer, and they're obviously not integers or fractions. They're not rational, and they won't show up in this list at all. This is just a list of what the rational ones will look like, because the rational ones are going to be the ones that we're going to be able to factor out nicely. So if there are rational zeros, they're going to be inside that set, essentially. That set of, there's 8 and then times 2 because of the plus minus, so there's 16 possibilities total. Even going beyond the irrational ones, there's something called the complex numbers where you'll actually probably find most of the zeros of this function, but that's a topic for a different course. So we won't worry about that too much here. So we're just going to do one more question. All right, so for this one last question, I'm going to give you this polynomial p of x. So it's a cubic polynomial, so 3rd degree. So we're not going to be able to use any of the factoring or quadratic formula techniques that you would have learned before. And so yeah, so we're going to actually use this theorem here. And that the little tidbit I gave that there will be at most 3 zeros to try to figure out what these actual zeros are. So we're going to use the theorem to list the potential rational zeros. And so there'll be factors of 6, basically, that last number, constant. So plus or minus, and the things that go into 6, it's 1, 2, 3, and 6. And now to actually finish the problem, I'm going to also use the fact that it is third degree, so there's at most 3 zeros. And we'll see a little bit, we'll talk about that a little bit more when we start mixing a couple of techniques together in the last lesson. We've got at most 3 zeros, and so we should be able to just go ahead and find them. So what we're going to do is find them by plugging in the potential zeros, because our zeros that we're looking for have to be in that list. Oh, I keep writing R first. And so you just do it one by one. I'll have P of 0 is, not P of 0, so P of 1 is the first one. And so I'm going to plug it in. 1 minus 2 minus 5 plus 6. Yeah, that's actually 0, so that's good. I've got x equals 1. I can do P of negative 1. I will get negative 1 minus 2 plus 5. So just the odd powers of x will change sign here. Plus 6. That's 11 minus 3 is 8. So that's no good. We'll go on to the next one. 2, P of 2 is going to be 8. Minus 8 minus 10 plus 6. So that's no good. That's 0. That's minus 4. Sorry, that looks like it says 8x. I wanted that to be like a 8 no. So maybe I'll put a sad face as it's a little, doesn't look like x. Yeah, so a negative 4, that is not 0. So that 2 is not a 0. P of negative 2. So again, it's only going to flip the odd signs. Negative 2 cubed is negative 8. Minus 2 times 4. Negative 5 times negative 2 is plus 10, and then plus 6. So we get 16 minus 16. That is 0, so that one's good. And then finally, we're looking for the last one, so we'll see what we get here. P of 3, just making my way through that list, is 3 cubed is 27, minus 2 times 9, minus 5 times 3, plus 6, and so I get 9, minus 15 is negative 6, plus 6 is 0. And so I get, yeah, x equals 3. I did say specifically there are 3 of them, so we can stop here. And so the 3 zeros are x equals 1, negative 2, and 3. And this should actually tell you how this thing factors. If you are curious, it's a little bit of a hint as far as how we'll mix different tools together to make this work a little bit faster. We could actually write that P of x is, since we know those zeros, x equals 1 gives us an x minus 1 factor. Negative 2 gives us an x plus 2 factor. And 3 gives us an x minus 3 factor. And the answer we were actually looking for is the list of zeros, but this just kind of tells you what the polynomial actually looks like. And then, I mean, you could actually multiply that out if you like and verify that we do get the function above. You can at least see it should be true with multiplying the constant numbers together. Negative 1 times 2 times negative 3 is, in fact, plus 6. So this is one method that we do get to use to find all of these zeros. We're going to look at next the polynomials that are not monic, and then just sort of combine some of the division that we learned in the last section with this polynomial construction to hopefully save us from having to do this great big huge list every single time.